Edgar. Yes, I also want to thank the organizers for kindly giving me this opportunity to present my work here. And what I'm going to talk about, in fact, has a lot to do with our previous speaker. And there might be a few things here and there that you will recognize along the road. So just to set the stage again, I'm also looking at a turbulent system where we have these energy cascades. For the purely 3D turbulent case, we have the direct cascade. Energy is somehow injected at large scales, moving down to smaller and smaller scales. And if we now reduce the system to a perfect 2D state, then you will kind of see the opposite, where turbulence is forced at some scale, and then energy can be transferred upwards. And if you don't take any measures here, these larger scales can actually keep on growing, and this typically results in the kinetic energy piling up at the largest available scale. And typically this results in a strong domain-filling large-scale vortex. Now, I'm actually inspired by systems like these. We see a lot of these systems in nature where there's vast flows that are clearly turbulent, but somehow the turbulence is constrained, and this is leading to the growth of these large-scale vortices. So we have seen these tropical cyclones, but also the big vortices on Jupiter and the like. And of course, this constraining can be one of many things, and probably many at the same time. Like typically the Earth's atmosphere is very thin compared to the horizontal dimensions. There is rotation due to the planet is rotating, and of course also density stratification effects might come into play. So all of that can be at stake here, and I'm going to look at the case where the turbulence will be constrained by rotation only. Now, what do we can clearly see these vortices in these types of systems, but it would also be nice if we can somehow predict what's going on in systems that are somewhat harder to diagnose. For example, this is Earth's liquid metal outer core, and this consists mostly of liquid metals, and the flow inside this layer is somehow the source of the magnetic field of our Earth, and we would like to be able to predict what type of flow structures we can expect there, because they are undoubtedly related to the shape of the magnetic field. So this is going to be my system that I'm going to investigate. So it's rotating Rayleigh-B&eacute convection. We have a plane layer of fluid which is heated from below, cooled from above, and then rotated about a vertical axis. For most of this talk, I will be discussing numerical simulations, and in numerical simulations, you can make this simple proxy system where there's no lateral confinement by just making the horizontal directions periodic. So we don't enforce any walls on the side. In experiments, however, we need to put some bounds on the system, and then this upright cylinder is the most popular geometry. So to describe this system, I'm going to use some dimensionless parameters. The first one is the Rayleigh number, which is actually directly proportional to the temperature difference that is applied over the fluid layer. So this is our forcing parameter. And the rotation will be characterized with the Ekman number, which is the ratio of viscous forces over Coriolis forces. This means that if rotation is strong, this will be a small parameter. And given that we are talking about thermal convection, we will also need the Prandtl number, and this is the ratio of momentum diffusion over thermal diffusion. So this tells something about the diffusive properties of the fluid that we choose to work with. So with all this in place, I'm going to study the growth of these large-scale vortices in numerical simulations of rotating convection. I will be paying close attention to the nature of the transition towards this large-scale vortex growth. We will see that it's not present in all regions of the parameter space, but only a specific region. I'm going to furthermore focus on the effects of boundary conditions, because in these numerical simulations we are free to choose any boundary conditions we want, but in experiments we are typically stuck with no slip walls, and they're actually turning out to have a big influence there. And then finally, what about experiments? I'm an experimentalist at heart, and I've been doing experiments for quite some time now on this system, and I would really like to study this process of this formation of the large-scale vortices in experiments, and I will give you an update on what's going on there, why this is so difficult in experiments in particular. So, on to simulations. So we are going to take this, this model of a stress-free, a rectangular box with stress-free plates to start with. This is a popular geometry, and many people have actually done these types of simulations before me. There's the group of Keith Julian, who actually did simulations of not the full equations, but an asymptotically reduced set of equations, meaning that you basically take the limit of rotation towards infinity, so rotation is surely dominant, and then you can simplify the governing equations a bit. The two other papers that I list here actually do use the full equations, and they have all seen the generation of these large-scale vortices. Now, just to give an idea of how these things look in these systems, this is taken from the paper by Céline Gervily, and this is a cross-section, a horizontal and a vertical cross-section through the domain, showing the vertical component of vorticity. And it's clear here there's this big red blob that is the main large-scale vortex that's generated in this system. And vertically, we can see that everything is nicely organized along the rotation axis, as we kind of expect in these systems. So this is a predominantly two-dimensional structure, as also already introduced by the previous speaker. So the next diagram I want to show is actually taken from the other study by Favier et al. And they actually gave a phase diagram of what to expect where. So we have on the horizontal axis, yeah, this is the Taylor number, is another parameter to describe the magnitude of rotation. It's 1 over Ekman squared, meaning that rotation actually increases to the right. And on the vertical axis, we have the Rayleigh number, or the forcing parameter. So one thing to first mention is here, this gray triangle on the bottom. This is actually the region where the system is linearly stable to convection. So there will not be any convection here. And the upper limit here, this line, that's the result from linear stability analysis done by Chandrasekhar. So only when we cross this line will we see the formation of the start of convective flow. Now, and Favier et al. Have covered this parameter space with some simulation points, and they saw the large-scale vortices appear in this green area. To note, we actually need to move a bit up from the linear stability limit by about a factor 2 to 3 in Rayleigh number. Then all of a sudden we see the onset of these large-scale vortex that they start to form. But if we keep on increasing Rayleigh beyond this number, then we can also see that there's an upper limit in terms of Rayleigh for which these vortices form. So one way to interpret this is we probably need a certain degree of turbulence, a certain degree of turbulent activity before the upscale transfers are manifested. And likewise, if we increase the forcing parameter even further, that at one time the forcing becomes too strong for that applied rotation rate where you lose rotational constraint, and then the upscale transfer also vanishes. And then one final remark is that we can see that some minimal amount of rotation is actually required to even see this, this process at all. So these are the take-home messages from these first papers. And then we came in, actually this is the work done mostly by Xander de Wit, who is also in the audience. We took the same parameter space, now in terms of Ekman number, so I apologize. Now rotation increases to the left. The language of choice keeps changing a bit throughout in this field. But what we were interested in is actually to really pay close attention to these transition ranges. So we see there's a transition at the lower Rayleigh number end, and then of course a transition at the high Rayleigh end. And we did many simulations with very small spacing to really see what is happening at these transitions. And here the parameters are shown, and I can say that these are very moderate for these types of simulations, so that we can actually also afford to do many different cases, and also very long simulations. So what does this look like? Well, this is a movie. We could see that there's a certain initial state with some randomness to get the convection going, and pretty soon you can see that this thing starts organizing. The cyclonic, so the positive vorticity patches, are actually the red ones, and they start to form and then merge into larger and larger structures. And if we wait for a bit longer, then we can see that there's really one big dominant red patch emerging from this initial chaos. So around this time, the two big ones will now merge, and you can really see that this thing has organized itself. So to get some quantitative information, we actually did this 2D, 3D decomposition that was also introduced by the previous speaker. So what do we mean by 2D? It means that we will take a vertical average of an instantaneous flow field, and this will be our 2D component. And then the remainder, those are now named the 3D fluctuating state, let's say, around the dominant 2D structure. So for a typical simulation, I show here the kinetic energy as a function of time, where we split up the total energy into the 2D mode, this is the yellow color, and then the 3D contributions also split up in horizontal and vertical contributions, where it's pretty clear that actually these 3D components remain sort of constant over the entire duration of the run, while the 2D component, so this big flow, this big vortex underneath, is actually growing significantly up to a point where it finally can saturate, and in that state we can see that there's clearly much more energy in this big 2D vortex than in any 3D fluctuations. And we actually decompose this into its this 2D energy into its Fourier modes, and the evolution over time then looks like this, where it's clear that the k equals 1 mode, the largest wavelength, fitting exactly in the box size, really contains by far the most energy. So this is this large vortex that clearly shows this one wave number. And in fact, in the end, in the final state, we can see that there is about a factor 30 between the energy in the k equals 1 and k equals 2 mode. So this is definitely the dominant one.
It's a square box. I mean, in what sense k? In kx, ky, or in...
Kx, ky, indeed. Yeah, it's a square box. From the top, square, yes. Okay, so some typical images. At this time in the evolution, there's not a real trace of any large-scale vortex yet, but the first, gathering of energy can already be observed, even though not from this instantaneous snapshot. But later on, it's pretty clear that indeed this thing is developing into this very big positive patch of vorticity. Now, we can also look at this in a different way by looking at the energy transfer among these Fourier modes. And this is presented here in these diagrams. So these diagrams actually show the transfer of energy from a mode Q to a mode K, which is then on the other axis. And this is actually split up in also in the 2D and 3D situation, where this diagram considers the interactions between the 3D and the 2D component, while this one is the interactions, the transfers within the 2D mode only. Now, looking at this right graph first, This diagonal is, of course, quite interesting to see. And this is a direct cascade of energy, because if we take some mode Q, we can see that it transfers energy to a mode K, which is one higher in wave number. So this is a step-by-step transfer of energy to higher and higher wave numbers, to smaller and smaller spatial scales. So this is what in the homogeneous isotropic turbulence would be the direct cascade. And the other important thing to notice here, what's happening on the axis. So we can see that both within the 2D mode and in the transfers between 3D and 2D modes, there's actually a transfer of energy from many modes Q towards K equals 1. And this is a direct transfer of energy. There is no real step-by-step, so this possibly is not best labeled as a cascade, but it's a direct transfer. All scales are actually contributing in transfer directly into this biggest available mode. Now we can further quantify this by just adding up all the contributions in this to this first mode, and this will be the energy transfer into that mode. So now we are ready to have a look at this the transition in a bit more detail, and I will start with this low Rayleigh transition. So this is where we are transferring from a state where there's just enough turbulence there to set up this whole energy transfer process, and then moving towards the large-scale formation, the formation of large-scale vortices, which is then on the right of both these diagrams. So, and first I show the ratio between 2D and 3D energies, and on the right, this is the upscale transfer of energy into the K equals 1 mode. Now, in both cases, we can see that on the far left, at small Rayleigh numbers, these quantities are both basically zero, so there's nothing indeed developing towards a large-scale vortex. But as you increase the Rayleigh number, there is some gradual growth, and then suddenly this big jump. Now, the big jump is also present in this upscale transport into the K equals 1 mode, and of course, exactly at the same position. So we can see that this big jump would also again indicate that this is probably a sharp, possibly discontinuous jump into this large-scale vortex formation. Now, you may wonder about this tiny little growth down there, where we are not quite ready for the jump, but still something is happening already. And in this case, it turns out that the flow is definitely showing some organization already, but it's more into a state of alternating jets. As you can see, this develops into a state with jets that moving in opposite directions, and sometimes they actually switch between either X or Y direction, and this is switching sort of randomly. So what that means is that there's also definitely an effect of the box. The periodicity is definitely felt. So, and then the situations just beyond the transition. So these we also studied in a bit more detail, and this is actually showing very similar dynamics as was shown in the previous presentation, where we can see that the flow typically reaches this intermediate state, which is actually just this alternating jet flow that we saw just before. And then it's just waiting for this final little trigger to be able to cross over to this large-scale vortex flow. And we did several simulations, and you can see indeed the moment of transition shows a clear distribution. And in fact, past the jump, we can see that the final state is actually nicely aligned again at a very similar energy. So there's a metastable intermediate state, and it's just waiting for the trigger to happen. So to get a better feeling for this, we did an ensemble of 100 simulations of this system, and sometimes they would take quite a long time. And but eventually we could get some analysis of the statistics of these jump times. So we would consider the time that the system spends in this intermediate state and try to get a feeling for the distribution of these waiting times. And this is shown here on the left, where the cumulative distribution turns out to be this nice exponential curve. And the conclusion there is that this exponential distribution of the waiting time signifies some kind of nucleation and growth dynamics. So the system is there and it's just waiting for this final trigger, this turbulent fluctuation that is strong enough to push it over the hill, and then it can go. And this growth process is further self-enhancing. So then it's time to move on to the transition at higher Rayleigh numbers. So this is where, in fact, the forcing can become too strong to overcome rotational constraint. Now, I once again show this kinetic energy ratio between 2D and 3D modes and the transport of energy into the k equals 1 mode. And now we see a distinctly different type of situation where there's a clear hysteresis going on. So if I start from the left with a large-scale vortex as a starting point, I can maintain the large-scale vortex for quite some range in the Rayleigh number until there's some moment where indeed this finally vanishes. And likewise, if I start off with a situation that is just beyond the transition, where there's no large-scale vortex, this thing will be sustained for quite some time downward. And this is this very nice hysteresis loop that is described here. And it's also perfectly mirrored in the upscale transport. So I have to say that this bistability between a large-scale vortex state and a state without a vortex was also observed by Favier et al. In an earlier paper. So this is a sort of extension of that work. So, but these are nice stress-free boundary conditions, and as an experimentalist, I'm a bit worried about those. I cannot really replicate those that easily. So,
Sorry, Rudie, can I just
yes.
ask a question? What saturates your LSV growth in the case of free slip boundary conditions?
Yeah, so there's no other possibility than that it's some kind of viscous action acting on the larger scales, that there's the gradients of velocity become large enough that this still becomes a dominant term somehow. I would say that's the basic mechanism.
I mean, it's the only plausible mechanism,
Yes.
but have you kind of looked at this in more detail, what actually generates this enhanced dissipation that's required?
No, we haven't looked at this in detail, I have to say, no, but will turn out that for no slip this will be different.
Yeah, well, that's what I'm asking.
Yeah. So, no slip conditions, but let's keep the periodic domain for now because that's still quite convenient. So, in some previous work that I did a while ago, we saw a significant effect of the boundary conditions. So this is for the exact same parameters, a stress-free case and a no-slip case. Well, clear large-scale vortex once again. In the no-slip case, none at all, none to be seen. So this was a bit of a puzzle, and also by the numbers here, we spent quite some effort in getting to some parameters that are a bit more extreme in that regard, but we could not get to any large-scale organization when there were no slip conditions. So now the question is, what is the big difference? Well, we answered this by the formation of Ekman boundary layers. Maybe familiar to some of you in the audience. Whenever there's no slip plates in a rotating flow, we typically see Ekman layers being formed. And these Ekman boundary layers have properties that are quite distinct from the regular Prandtl type boundary layers that we often encounter. And for one, the thickness of the layer is actually purely set by the viscosity and by the rotation rate that is applied. And that means that things like height or the bulk velocity above the boundary layer do not play a role in setting the thickness. So this is quite unique for boundary layers. And a second key property is the phenomenon of Ekman pumping, as it is typically called. So you can solve the equations that describe this boundary layer, and they will show you that there is a direct link between vertical velocity and vertical vorticity, let's say at the edge of the boundary layer, so just above here, like let's say. So whenever there's, in this case when we are close to the bottom plate, whenever there's upward velocity, there should also be positive vorticity, and vice versa. So this is kind of schematically shown here, and we can draw similar conclusions for the top plate. And this condition means that whenever there's a thermal plume being formed, where there's some bit of convergence of hot fluid close to this hot plate that emerges vertically into the domain, it will gain positive vorticity. Positive vorticity together, this leads to a whole bunch of small-scale vortical plumes that keep emerging from the boundary layers, and they are actually perturbing the bulk. So I need to note that this is symmetrical also from the top. We have similar situations where cold plumes are actually also getting positive vorticity and penetrate into the bulk. So these are small-scale effects, and they actually prevent this large-scale organization in some way. So we were trying to still get some large-scale vortices in this no-slip system, and we decided to just go ahead and push the parameters even further to see what we could find. We tried two different approaches, in fact. The first one is to really push the Ekman number down, so we are going to be more and more rotationally constrained in a way. That also means that we needed to go up in Rayleigh number because we still need this turbulent flow. Now another approach, which is maybe not immediately obvious, but we tried also to go to a low Prandtl number fluid. So low Prandtl number fluids are also relevant in these kinds of systems. Liquid metals have a very small Prandtl number. So we decided to move to Prandtl 0.1, which is not quite in the range of liquid metals, but it's getting there, let's say. And the reason to do this is that thermal plumes will be less coherent in this range because the diffusivity of heat is much higher, meaning that whenever there's this blob emerging, it will also rapidly get rid of its excess heat by diffusion. So these disturbances are less coherent. And this indeed allowed us to get to large-scale vortices also with no slip plates. So the first thing that we did was to push the Ekman number down to approximately 10⁻⁷. And then we could indeed see large-scale organization, but now with a dipolar large-scale vortex instead of just a single one. And it's clear from the picture alone that the cyclone is still quite dominant compared to the anticyclone, but they are both definitely there. Now, what could then be the difference between these two states with just a single vortex or two? And this was actually treated in a paper by our previous speaker already, where they considered two different saturation mechanisms of some kind. So it can be that even viscous action at the larger scales becomes large enough to saturate the energy, which means that the cyclone and the anticyclone could coexist in this range. So this is again a situation where this large-scale viscous action must somehow be present. And the other situation is that when there's not enough friction in a way that the anticyclone actually dies because of its own success, right? If the anticyclone starts spinning against the direction of rotation that you apply with enough magnitude, you can actually cancel the background rotation in some way, and then the anticyclone will vanish completely. So that's the other situation that was described there, and we can observe both of them depending on the parameters. What I also need to emphasize is that to get to this large-scale vortex, we actually had to go to Rayleigh numbers that are much farther above the critical onset point of convection, because for stress-free you could see that 2 to 3 times critical Rayleigh number would be enough. Here we actually need to go to 50 times the critical Rayleigh number before you can even observe this, this large-scale vortex formation. So then the other approach to move to low Prandtl number fluids, this would also give a very nice large-scale vortex once again. I actually put no slip and stress-free side by side so that we can also see the differences. And it's clear that the stress-free case is much more well developed. It has also more energy contained inside compared to the cyclone for no slip. But they are definitely both, clearly being developed and present. And in this case, we can also see that the critical Rayleigh number needs to be surpassed by less to get to large-scale vortices. In fact, we could also get to the upper limit, so where the thermal forcing becomes too strong for the rotational constraint to remain there. So then, next question, what about experiments? So there has been a trend in this field of rotating convection of moving towards ever taller but slender convection cells, because this helps to reach high Rayleigh numbers and low Ekman numbers at the same time. You only need to look at the definitions of the two parameters to see that indeed, if we want to have high Rayleigh numbers connected with low Ekman numbers, height is the obvious first parameter. So in this overview that we did, discussing some of the available experimental setups, you can immediately see that these things are indeed slender and tall and moving up to 4 meters. So this is the convection setup that I built in Eindhoven, where we can have heights of up to 4 meters while having a diameter of only 40 centimeters. Now we can also see that quite a few working fluids have been used in these different setups, so we can also cover quite a bit of Prandtl number range in that case. But this slender domain, it may not be the smartest choice in the end, because well, we built this setup, we did some preliminary measurements, and we were comparing to some results that were available in the literature. So we have we measured the convective heat flux, which is here shown in a dimensionless form as the Nusselt number. We did this at a constant Ekman number, constant rotation rate, and we changed the Rayleigh number. Now, in this diagram, I've shown some experimental results from a previous experimental study. These are the yellow squares. The blue diamonds are the results from our newly built setup, and they nicely match, so this was good. And we actually compared to two studies in which direct numerical simulations were involved on the periodic domains. And then, well, we cannot really cover this branch that well with experiments, but right here, well, this was promising. Results were kind of overlapping, but then here they finally branched out, they spread apart, and you can see that there's actually a gap of about a factor 2 between the cylinder domains, this is the upper branch, and the periodic domains, this lower branch. And then we asked ourselves the question, what's going on here? And then we decided to do some simulations in a cylinder to just check what's going on. And this is going to be the result. So what I'm going to show is a cross-section at half height, horizontal cross-section, showing vertical component of velocity. So this is at a relatively low Rayleigh number. And yeah, some things are already quite remarkable. You can see that close to the sidewall, there is this layer where actually the highest velocities are being found. This was quite unexpected. You would say close to the wall, there's a lot of friction. This will certainly not be the place to have the highest velocities. And we can see that there's this very nice division into one half of the circumference having downward velocity and one half having upward velocity. And this thing rotates against the direction of rotation that's applied. Now the next remarkable thing is where the two halves meet, you can see this constant injection of some kind of radially inward jets that are actually perturbing this bulk flow quite a lot. And this all is a bit less clear in the more turbulent case, but you can still see the organization with one half being the downward flowing. This one is the upward flowing and the other half is the downward flowing, also still showing this gradual precession, and the radially inward jets, all more turbulent but still present. Now, this turns out that the contribution of this so-called wall mode to the heat flux is actually quite significant and remains significant even when we are in this turbulent bulk state. So the active convection mode near the sidewall is actually quite important in these kinds of systems. And the presence of these modes has been known for quite some time from experiments in the 1990s. Turns out if you do convection in a cylinder and you start from 0 temperature difference, then build up, the first mode of convection that will become unstable is this mode near the sidewall. That's here shown in this shadowgraphy image. So if we were to have a movie of this one, you could see the black and the white spots also rotating. And this is a mode that onsets before the bulk becomes unstable. But this was well and all, but nobody actually expected this thing to survive well into the turbulent regime. But indeed it does. So around the same time as we observed these things, other groups also shown similar results. So these are simulations done by the group in Göttingen, or Zhang et al. And these graphs show actually time histories of the signal around the circumference of the cylinder, in this case temperature at half height and vertical velocity at half height. And this once again clearly shows that the circumference is covered by one part upward flow, which is a bit hotter, and one part downward flow, which is colder. And this pattern is actually rotating against the direction of rotation that's applied. Likewise, in a numerical study where also Edgar was involved, they found similar results, and they also saw that the actual shape of the container does not matter at all. Even if you make this Pac-Man type shape container, the wall mode will not care and just go along the sidewall without any problem. So turns out that in these experiments, now this wall mode is actually ruining everything for us. These inward protruding jets, they completely destroy any organization into large-scale vortices that might be there otherwise. So next step is that we hope to be able to somehow suppress these wall modes from even becoming active. And for that, there has been a recent study where also Edgar was involved, and they propose to put some kind of horizontal fins on the sidewall to try and block this wall mode. So they actually tried two different setups, where you would apply a fixed temperature boundary condition on this barrier, and the other where in fact the barriers could be made of conductive material, but would still be solid. And this would be the easier option to implement in an experiment. So think of some kind of ring-like shapes at the sidewall to block this wall mode. And they've tried this in a geometry that resembles a channel flow. So this is a top view, where in this case, in the first picture, there would be periodic boundary conditions in both directions. So this is let's say, the natural state of convection without any influence of a sidewall. Now, this is the result for the channel geometry where there are sidewalls. So we would have solid walls in these directions where there could be some kind of motion along the walls. And indeed, we immediately see the formation of these wall modes once again, where they would actually be traveling up and down in this direction. And then the final image is with walls and barriers to try and stop the wall mode from forming. And well, we can see that at least qualitatively so far, these things are similar again. And they also showed that if you use the appropriate number of walls, you can even recover global statistics like the heat transfer, the Nusselt number. So we now hope that we can implement these kinds of features into experiments to also have an experimental situation where we can study bulk dynamics without the influence of the sidewall modes. But that's where we are right now. So let's conclude. So we've studied the LSV growth, the growth of these large-scale vortices. It's found in a confined range of Rayleigh numbers, where there's nucleation and growth dynamics triggered by some strong fluctuation to cross the barrier. And at the high end of the Rayleigh number, we can see the nice hysteresis loop between a vortex state and a non-vortex state. Boundary conditions are very important because these Ekman type layers, they introduce perturbations that stop large-scale vortex growth. And if you have a sidewall, then things can turn out even worse because these sidewall modes, they can ruin the party for you. So with that, I would like to conclude and also thank you and thank my co-workers on these projects.
So thank you, Rudie, for a wonderful talk. Talk is now open for discussion. Yes.
I have a question on the aspect ratio of your domains. So you're saying that if the aspect ratio is small, you have the issues with the wall mode.
Yeah.
I mean, maybe it's complicated, but why didn't you just go to a large aspect ratio?
Yeah. So this is a particular important question for experiments. I have to say we are constantly dealing with some kind of limitations because we want to study this so-called geostrophic regime of convection where rotation is dominant, and this requires very small Ekman numbers. And next to very tall setups, that also means that rotation can be quite strong. Unfortunately, there's also this effect of centrifugation. We are looking at a buoyancy-driven system, and nowadays we typically use the limitation that centrifugal acceleration should be at most, let's say, 10% of gravity to still have a sort of reasonable system. Of course, if you would make the thing wider, this would get bad really quickly. Yeah.
Bruce.
So what sets the radial scale of the wall mode, and does that vary going from the top to the bottom?
No, they are actually remarkably uniform in thickness, and in fact, from the theory that was developed also in the 1990s, it is clear that it scales as the Ekman number to the power 1/3. So we have also a very good prediction for the thickness. So that's the good thing. We know what we are dealing with, kind of.
Okay. And you showed at one point temporally they go anticyclonically around.
Yes.
But at a snapshot in time vertically, does it spiral around or is it coherent top to bottom?
I think it's coherent. Yes. will be, yes, it is coherent indeed, yeah. Yeah, even though quite turbulent and fluctuating, as you could see also in these time diagrams, right?
Pat? So is the process of the growth of the LSV, once you hit the critical Rayleigh number in energy piles to lower Q, it looks awfully like a rapid distortion type of process. Is that in fact what's going on, and is the criticality condition achieving a sufficient, say, shear in the LSV to eat all the other energy?
This is a question that we did not look into much yet, but I'm eager to hear about these what you are just.
I mean,
specifying.
because it has the signature of it, right? Kind of non-local transfer and all the energy piling into one state like that.
Yeah. Would be interesting indeed. Yes.
Brad?
This wall mode appears to have a topological origin, at least in the linearized approximation. So from that point of view, it's maybe not surprising that you have to go to some lengths to suppress it. But it is quite interesting, and it might be worth investigating experimentally for its topological properties. There's a paper by one of Edgar's postdocs that's looked at this recently. It's on the archive.
Yeah. Yeah, thanks. Yeah, indeed. Yeah, there's a lot that can be done there still. That's sure. That's true. Yes. So I'm yeah, definitely looking into that. But well, experimentally, it's a bit tough to vary aspect ratio at will, for example. But indeed, numerically, we can do these things.
Experimentally, if you can get enough measurements of velocity, you may be able to directly look at this a winding number associated with the topology. But I'd be happy to chat with you.
Oh, thanks. Yes.
Pascal?
I want to go back to the first part of your talk where you looked at the LSC formation. You were talking about these alternating jet state as
Yes.
a metastable state. My understanding is as soon as the aspect ratio is not exactly square, that actually becomes the preferred state rather than the large scale vortex. So is it only metastable in the square case, and then other than that it becomes dominant? And if that's the case, what's the transition? Does it become a first order or second order?
Yeah.
In
So
the nomenclature that Alex was talking about?
yeah, indeed. So there is indeed this this transition. If you make the domain slightly longer in one horizontal direction, and this is only a few percent that is required, then suddenly the system locks into this alternating jets, basically, and there's never any large-scale vortex appearing. And this transition has not been very well studied yet, I have to say. There's a few works that have considered some of this, so I cannot answer the question, but it's definitely something that's still quite interesting to have a closer look at, indeed.
I think there will be a talk on this topic later in the workshop by Adrian van Kaan. Adrian?
Thanks for the very nice talk. I was curious about, so you had the low Rayleigh number, what you call nucleation type dynamics, and then in high Reynolds number you had the pure hysteresis. So in the thin layer turbulence case, there are transitions from the 3D turbulence to the large scale vortex and vice versa. But do I understand correctly that here you never jump back from the vortex? Once it's there, it never collapses back into 3D turbulence in the low Rayleigh number?
Well, up to given time that we can simulate, this does not really happen, no, indeed. Yeah. So this is always in the back, perhaps later, but these things also run for a very long time, so you never can be 100% sure, but we haven't observed it at least.
And the follow-up, so in the high Rayleigh number hysteresis case, there are just no spontaneous transitions between the two branches. If you start with the large scale vortex, it remains.
Yeah, it looks to be quite stable indeed, that there's no sudden jumps, but once again, also there we cannot be 100% sure. Even though, yeah, by this mechanism you might expect that it could also happen here. Yeah.
David?
You mentioned the Prandtl number for the no slip case. Do you know the Prandtl number dependence for the stress-free case? Is Is it easier to form LSVs at low Prandtl number in that case?
Yes, likewise, indeed. Also, for the stress-free case, it's way easier to get a low Prandtl number condensate vortices than high Prandtl number. Yes. But yeah, it's hard to really give a quantitative answer, but this is the qualitative answer that we've seen by comparing Prandtl 0.1 and 5, let's say, which is for water. Rich?
Yeah, what happens to the Nusselt number when you get these LSVs? Does it go up or does it go down?
It barely changes. That's quite remarkable.
It changes.
Yeah, yeah. So this has been investigated by this paper, in this paper that I cited by Céline Gervely, 2014, and they saw a slight reduction in the Nusselt number when the large-scale vortex is formed, but this is like some percents compared to the case without an LSV, and so there's no big difference, certainly nothing that can be clearly observed at least.
A follow-up. So when that happens, where is most of the heat transfer take place? Where the vortex is, or around it where the anticyclone was supposed to be?
Yeah, around the vortex, indeed, yes.
Most of the heat flux happens around the vortex?
Around the vortex, not inside the vortex, indeed. Because there's no real vertical component associated with the vortex. That's the conceptual picture, let's say. Mm-hmm. So somehow, probably that means that vertical transport is somehow enhanced outside of the vortex to still have a similar convective heat transfer.
Okay, one last question, because we're basically at the end of the morning session. There a quick question from anyone? Laurette.
Well, between the horizontally periodic box and the cylindrical, the tall cylindrical domain, there's a lot of intermediate cases. In the horizontal box, do you allow flux through it, or is it periodic but with the box being the velocity having to be parallel to the walls of the box? For example, is it all the same height? What's the story?
Yeah, so in all of these periodic domains that I mentioned, it's truly everything is periodic. There's no sidewall condition other than we repeat everything there. In the cylinder, everything that I mentioned about cylinders has no slip on all sides.
So it's not confined in this periodic box?
No, not confined. Yeah, vertically, but...
Okay, well, I think this is a good time to end the morning session, so thank you again.